Welcome back to part 3 of the cardiovascular system, blood vessels, blood flow, and blood pressure. We are spending time on this. Heart disease is still the major cause of death for adults in the US, and it's important to know why. We're going to kind of veer off a little bit from talking about mean arterial pressure to talk about blood flow and exchange out of and into the capillaries, and talk about how blood moves in and out. I like this drawing because it is showing us a couple of things. This is a closed system, right? The cardiovascular system. Here is the heart. Remember, arteries are vessels that carry blood away from the heart. And so they're showing you the big elastic, the aorta, and then they're going to be branches, right? So we have branching, and then the muscular arteries, and they're going to branch, get even littler, and they're going to become arterioles, which is mean arterial pressure comes from. And off these arterioles is where we get capillary beds. Surrounding tissues and cells, right? So this is just showing you one capillary bed. There's lots of capillary beds going to all different areas of the body, exchanging with all different cells and all different tissue beds, but we're looking at one. Again, like I said, you have branching until you get to the capillary beds, and now you've just got a whole bunch of merging. Vessels are merging and returning blood to heart. And now we are just arbitrarily calling these vessels veins. Veins are vessels that are bringing blood back to the heart. But it's a closed system because that same blood comes on back to the heart. Here is where you have exchange. So stuff's leaving the capillaries: oxygen, glucose, sodium, potassium, ions, you name it. What's coming back in? Carbon dioxide, waste. So there's an exchange. Stuff's leaving, going out into the interstitial fluid here. And then the interstitial fluid's having stuff go back into the system. Here's where the lymphatic system comes into play. This is your lymphatic system. It is an alternate route for things that leave capillaries to then go through the lymphatic system and then get dumped back into the venous blood. So lymphatic system is an alternate route for some of the fluid that leaves the capillaries that doesn't get brought back into the venous end of the capillary. The lymphatic system is another route for that blood to, or fluid to, return to the heart. It doesn't have plasma proteins, so we don't call it blood, but it's an alternate route for fluid in the circulatory system to return to the heart. Again, though, it's still kind of dumping it back into that closed system. So the volume that you start with here kind of ends up with the volume you end up here, i.e. closed circuit. So capillaries are the site of exchange between the blood and the interstitial fluid. Remember, the interstitial fluid is the fluid that surrounds the cells. And the cells exchange with the interstitial fluid. and then the interstitial fluid exchanges with the blood. Low capillary pressure. Why? If there's high pressure going into a capillary, the capillary walls are super thin and really fragile. So if you have a high blood pressure, if you have a lot of pressure in that blood going into the capillary, it's going to destroy capillary wall, meaning capillary breaks. That's bad, right? Now you don't have a way to get that blood back into the venous end because there's nothing connecting the arterial end to the venous end. So high pressure, high blood pressure can cause capillaries to break. That's a problem. Walls of the capillary are very thin. There's going to be a very slow flow because they have a lot of them in a given capillary bed. So there's so much branching that it slows down the flow. They're very permeable, flowing through this area. So there is time for exchange with the interstitial fluid. There are precapillary sphincters that control the flow from an arterial through capillary bed. Remember active hyperemia. If your tissue is really active, these precapillary sphincters are going to relax. So you will have blood flowing through all of the capillaries. But if you're not metabolically active, these precapillary sphincters are contracted. And so the blood's just flowing through the tissue bed. You don't need all that blood flow. There's less blood flow to that tissue. Thus, there's less cardiac output to that area because the precapillary sphincters are constricting blood flow throughout the capillary. And so you have these meta-arterials. You're still getting oxygen delivered to this tissue area, but it's meeting the metabolic needs, which isn't much. So meta-arterials are intermediaries between the arterioles and the venules. And so they kind of function as a bypass when there is low needs in that tissue. When I say low needs, I mean, low oxygen needs, right? Because that's the main thing. The smooth muscle precapillary sphincters are going to contract and relax based on local factors, active hyperemia. And so when they contract, they decrease blood flow. And when they relax, they increase blood flow through the capillaries. Precapillary sphincters, they're going to contract and relax based on local factors only. And what are those local factors? An increase in the partial pressure of carbon dioxide, a decrease in the partial pressure of oxygen, an increase in the concentration of protons, which is a decrease in pH. These types of local factors are going to cause them to relax and increase blood flow. Under conditions where you have high partial pressure of oxygen, it's going to cause constriction of the capillaries, which will decrease blood flow. Bulk flow in and out of the capillaries themselves. That means just everything inside the blood in the capillary is going to be pushed out into the interstitial fluid. That is called filtration. That is movement out of capillaries into the interstitial fluid. And this happens on the arterial end of capillary. And then there's going to be absorption of fluid back into venous end of capillary. Remember, between the interstitial fluid and the blood. This is basically, if you look at it here, this is the capillary. This is the tissue bed. And you're going to have fluid being filtered out in bulk into the interstitial environment. And this is in the arterial end. And then on the venous end, you're going to have absorption back into plasma from the interstitial fluid. So you have to have everything being absorbed that was filtered out. It has to be absorbed somewhere. Otherwise, you're going to have edema or a collection of fluid just sitting in the tissues. And so when we look over here, this right here is showing you this is the interstitial fluid, and this is the plasma or blood. And you're seeing gases, fatty acids, steroids, hormones diffusing through. You have ion channels or glucose channels. You can have proteins being endo and exocytosed, aquaporins with water going through. These are the different types of things that are being exchanged across the capillary wall, which is very thin. What regulates this are forces, and these forces are called Starling forces. Starling was very busy in physiology. So Starling forces for bulk flow are two different forces. One is the force due to water, and so we call that hydrostatic pressure. Hydrostatic pressure is the pressure created by the fluid itself. Then we have osmotic pressure. You remember this. This is the pressure created by solutes that drive osmosis, which is the way water or fluid moves. And hope you remember, water moves up the osmotic pressure gradient. Water follows solutes. When there's more solutes, that's more osmotic pressure and it pulls water towards it. So hydrostatic pressure, osmotic pressure. Osmotic force exerted on water by the non-permeating solutes. Those are the solutes that cannot cross the capillary wall. And what are those? Those are plasma proteins. And these proteins are created in the liver. This is one reason your liver is extremely important for moving fluids around your body in and out of your circulatory system, is the liver creates plasma proteins for osmotic pressure. So here's the arterial end, right? You're going to have blood flowing through to the venous end. And so you're going to have hydrostatic pressure and osmotic pressure. Hydrostatic pressure is this P. This is hydrostatic pressure. This is osmotic pressure. This is hydrostatic pressure. This is osmotic pressure. So you've got two hydrostatic pressures. There's the hydrostatic pressure inside the capillary. Well, I should do this. Hydrostatic pressure inside capillary. So this essentially is the pressure of the fluid inside capillary. This right here. Osmotic pressure is the pressure of plasma proteins inside plasma. They're creating this osmotic pressure. Under healthy conditions, there should be no plasma proteins in the interstitial fluid because they're plasma proteins. That means they should be proteins only inside the plasma. So this osmotic pressure in the interstitial fluid should be close to zero. No pressure, unless you break capillaries. That's what bruising is. The capillaries open up, plasma proteins then go into the interstitial environment. And now you have osmotic pressure in the interstitial environment. And that's why fluid doesn't necessarily come back and stays out there. And we call it swelling. But there is hydrostatic pressure in the interstitial environment because there's fluid out here. Why am I telling you all this? Because when you see this, you're going to get nervous, but don't be nervous because it's really the same thing. You have at the arterial end, you have the fluid exerted. So this is the fluid pressure exerted by the fluid in the plasma in the capillary. It's 38 millimeters of mercury. There's no osmotic pressure in the interstitial environment because no plasma proteins to pull water towards the interstitial fluid. That's why it's zero. There should be no osmotic pressure in the interstitial fluid. So there's no osmotic pressure outside of the capillary. So there's 38 millimeters of mercury that is the pressure that wants fluid to leave, right? This is the pressure that is driving stuff to leave the arterial end of the capillary. But remember, there's a venous end here too. And so at the venous end, there is still not 100% of the fluid leaves the capillary. There's still some fluid in here. So there's still some fluid, and that fluid is still exerting 16 millimeters of mercury inside the capillary. So we have to take this and subtract the fact that there's still 16 millimeters of mercury at the venous end because not all the fluid left. And so that is where we are coming up with these numbers. On the venous end, fluid has left. And so there are plasma proteins with less fluid. And so there's going to be an osmotic pressure at the venous end. Goes up. Why? Less fluid, because fluid left. At arterial end. Interstitial hydrostatic pressure isn't much because there's so much more area. It's not confined to a little tube. So the hydrostatic pressure in the interstitial environment is zero. All right. Taking a step back and looking at this. Oops. It's now going to talk about arterial end, filtration, and absorption. So filtration is pressure for fluid to leave capillary. Most of it's driven by hydrostatic because there's no solutes in the interstitial fluid to pull water out into the interstitial fluid. So really, the drive to filter is all hydrostatic. Capillary pressure or pressure in the capillary. To reabsorb back. Arterial end of the capillary. There's plasma proteins exerting osmotic pressure in the capillary. And it's 25 millimeters of mercury. The hydrostatic pressure is a little bit pushing fluid back into the capillary. But when I say a little, I mean a little. It's 1. So really, the pressure to reabsorb is 26 millimeters of mercury at the venous end. That is when we're looking at this. This is the arterial end, and this is the venous end. The arterial end, there is 38 millimeters of mercury for fluid to leave, and then there's 26 millimeters of mercury for it to come back in. This is different at the venous end. Why? Because fluid has left. And so since fluid has left at the arterial end, there is less hydrostatic pressure. So decrease in hydrostatic pressure. So there's less pressure on the venual end for fluid to leave. So less pressure for fluid to leave, but more pressure for fluid to, and I'm going to say reabsorb back into capillary. Because this osmotic pressure is greater in the venous end because fluid left, and now you have plasma proteins or solutes closer together. And so they're increasing the osmotic pressure. Fluid left, those proteins got closer together or more concentrated. That created more osmotic pressure in the capillary. There's not a whole lot of pressure from the fluid in the interstitial environment because it's so much bigger, but there's 1 millimeter of mercury. So the absorption then goes to 26 millimeters of mercury. It's higher. So you have a higher absorption and a lower filtration at the venous end. Here you have a higher filtration and a lower absorption at the capillary end. These are the pressures that are driving. And so this might look confusing at first, but if you go through it and you start to master hydrostatic pressure, it's the force exerted by the fluid against the wall. In capillaries, this hydrostatic pressure forces fluid out, i.e. filtration at the arterial end. But as fluid leaves, that is increasing the osmotic pressure in that capillary, which then is the force pulling fluid back in at the venous end there. So looking at this now, this is going through the net filtration pressures, which is just the sum of them all. at the arterial end versus the venous end, and we kind of went through this. So it's really the pressures of filtration minus the pressures of absorption. And so this right here is supposed to be a little pi for osmotic pressure. And so at the arterial end, you have hydrostatic pressure minus osmotic pressure. There's still, if you take out the osmotic pressure for reabsorbing, there's still 12 meters of mercury that favor filtration at the arterial end of capillary. So what you are seeing is you have things moving out into the interstitial fluid at the arterial end. But as fluid leaves, there is an increase now in osmotic pressure in the capillary. And that osmotic pressure is going to be greater than the hydrostatic that's still in there. So the fluids that's still in there that wasn't filtered out, it still is not enough to overcome osmotic pressure to pull fluid back in. At the venous end. And so you're going to get reabsorption. It's 10 millimeters of mercury more to pull it in than it is to filter it out at the venous end. So you see that there is pressures to reabsorb. So osmotic pressure at the venous end is what pulls fluid back in. Hydrostatic pressure in the arterial end is what causes filtration out. And so this drives movement or bulk flow through the capillaries. Now, net filtration pressure is going to be filtration minus absorption because it's a net. And again, at the arterial end, hydrostatic favors filtration. At the venous end, osmotic favors absorption. But there's more being filtered than absorbed across the capillary wall. So each day, 20 liters of fluid is filtered out, but only 17 liters is reabsorbed. That means 3 liters a day is not reabsorbed into capillary. Where does that 3 liters per day go? It goes through the lymphatic system. So that 3 liters per day that is not being reabsorbed in the venous end is being absorbed into lymphatic system. But it's still getting dumped. Oops, didn't mean to do that. It's still getting dumped back into the venous system. Right here. Right there. So it's just an alternate route. Factors that can disrupt this filtration and absorption across capillary wall. Well, when you're standing on your feet, this all day or for long periods of time, it's going to increase hydrostatic pressure, which favors filtration out of capillaries. And so more fluid is in interstitial fluid. So it's gonna make that area swell, right? Injuries. Anything that increases the osmotic pressure in the interstitial fluid, meaning water moves into the tissues, because you broke a capillary wall, plasma proteins go into interstitial fluid. It's going to increase the osmotic pressure of the interstitial fluid from 0 to something. And so that's going to cause fluid to stay in that area because it's disrupting this osmotic pressure. Histamines also can increase the permeability to plasma proteins. So they get filtered into interstitial fluid. And so this increases the osmotic pressure of interstitial fluid, and it increases fluid in tissues, which we call swelling. So an antihistamine, it works against histamine, so you don't have swelling. Liver disease, the liver cells don't work anymore. They're going to decrease their production of plasma proteins, which is going to decrease osmotic pressure, which is going to decrease fluid reabsorption back into capillary, and it stays in the interstitial fluid. This is also swelling or edema. Kidney disease also can filter out plasma proteins in the urine. And so you're decreasing the plasma proteins into urine, so it leaves the body. This ultimately is going to decrease plasma osmotic pressure, and it's going to then decrease fluid absorption. That's why kidney disease, you're also going to see edema, right? You're going to see extra fluid in the interstitial fluid around cells or swelling. This also decreases blood volume, because as plasma proteins leave the blood, they're solutes, and so more water also leaves the blood, and so you increase your urine output and you have plasma proteins in your urine, but that's decreasing blood volume, and that can mess with blood pressure. So kidney disease, actually, you see if someone has a decrease in blood pressure, you start looking for these things. Heart disease, pulmonary edema, that's where you have a backup of fluid into your lung tissue. Why? Because left ventricular pressure, if it's too high, then it's going to back up the pulmonary circuit because less blood can make it into the left artery, or less blood is leaving the left ventricle, and so it's backing up the systemic or left side, which then makes it harder to put more fluid from the pulmonary circuit into the systemic circuit, and so it backs up into the pulmonary circuit, so you get pulmonary edema. Veins are very compliant. Like I said, they don't have a lot of elastic tissue. They will just keep absorbing more blood volume. Veins also rely on skeletal muscles contracting to squish them, to create more pressure, to drive that blood back up to the heart. So when valves start to break down, you can get blood just kind of sitting in those veins, and then the veins just kind of keep collecting blood, and then you start to see them. Those are called varicose veins. Other things that influence venous pressure, venous return, again, blood volume. If there is a decrease in blood volume, say you are hemorrhaging, blood, right? You're bleeding out. That is going to decrease venous pressure. You just have less blood, so it's decreasing hydrostatic pressure. If you increase blood volume, it's going to increase venous pressure, right? So long-term regulation of blood pressure is going to be through blood volume, which is really controlled by the kidneys. So kidneys are controlling. So if we're looking at this diagram, muscles contracting, diaphragm and abdominals contracting, those are going to squish the veins. So that increases pressure. If you have epinephrine, norepinephrine, making the smooth muscle contract in the veins, that's also going to create more venous pressure. If you increase the amount of blood in the system, increase blood volume, it's going to increase venous system. It's going to increase return back to heart. On the flip side, if there is a decrease in the activity, decrease in blood volume, it's going to end up decreasing pressure. And that is ultimately going to affect cardiac output. So wrapping this up, kind of tying this up with a bow. Determinants of mean arterial pressure, which essentially is your blood pressure. Determined by heart rate and stroke volume, otherwise known as cardiac output, times total peripheral resistance, which is really controlled by the diameter of the arteries. Blood flow, also known as cardiac output, is determined by your mean arterial pressure divided by the resistance in the system, or mean arterial total peripheral resistance. So again, putting these two together, we end up with this right here. Blood pressure is determined by heart rate times stroke volume times how much resistance in the system that blood has to overcome. What controls it? Autonomic nervous system, hormones, like antidiuretic hormone, like angiotensin. These are examples of hormones. What is regulating this moment to moment? And by the way, if your blood pressure is below normal, we call it hypotension. If your blood pressure is above normal, we call it hypertension. And so short-term regulations are really occurring via the nervous system. It's really the hypothalamus controlling epinephrine, norepinephrine. And this is affecting the blood vessels. Or there's direct neural control through the sympathetic nervous system directly to the SA node and AV node of the heart and to the myocardium. Those are all direct neural control. That is, turn on the switch, turn off the switch. But long-term regulation is really controlled by blood volume, and that is determined by the kidneys. And what controls this are hormones. And so we really get into this in chapter 18, right? So that's the urinary system. So that's how the urinary system controls blood volume, which affects our blood pressure. And this is hormonally regulated. The short term, generally speaking, is regulated by the nervous system. And the nervous system is kind of monitored by receptors. And so these receptors for monitoring the pressure in our cardiovascular system are located in the aorta here. So they are aortic baroreceptors, as well as in your carotid sinuses. This is where the carotid artery splits into the internal carotid artery and the external carotid artery. And there are receptors that are monitoring the pressure, and how it monitors pressure are baroreceptors, which respond to being stretched. So if there is an increase in pressure, it is increasing the stretch of the receptors. So these baroreceptors are responding to stretch, increased pressure, increased stretch. And that is going to activate the autonomic nervous system. Now, the autonomic nervous system is parasympathetic and sympathetic. So rest and digest and fight or flight. The parasympathetic is shown in blue, and it innervates the SA node and AV node for control of heart rate. The sympathetic nervous system also affects the SA node and the AV node, but also controls the heart muscle or myocardium to increase muscle contractility or increase force of contraction. And you're like, okay, what does that mean? Well, that means a higher stroke volume. You contract more forcefully, you eject more volume of blood. So let's go through this. Parasympathetic input to the SA node, actually the decrease in firing of action potentials to the SA node is going to decrease heart rate. Sympathetic, the increase of firing to the SA node is going to increase heart rate. If it's going to constrict arterials, it's going to increase resistance. It can also increase vasomotor or venomotor by increasing the smooth muscle of the veins as well. Now, the baroreceptor reflex is exactly these receptors responding. So here it is, simple as this. You have an increase in blood pressure quickly. Your receptors in the carotid and aortic sinus sense this increase in pressure and increase in stretch. So there's an increase of stretch. Those receptors then send action potentials to the cardio centers in the brain. And it's going to do two things. It's going to inhibit the vasomotor center, and it's going to stimulate the cardio accelerator. So what does that mean? Well, there's a cluster of sympathetic neurons in the medulla oblongata, your brainstem, that oversee changes in blood vessel diameter. So that's vasomotor. But the cardio centers are also going to cause a decrease in the sympathetic impulses to the SA node, which is going to decrease heart rate. And then it's decreasing action potentials to the heart muscle. And that's going to decrease the contractility. It's decreasing stroke volume and decreasing heart rate. Therefore, it is decreasing cardiac output. Decreasing cardiac output. In addition, it's decreasing the rate of impulses going to the smooth muscle of the arterial wall. And so it's vasodilating. It's decreasing the impulses. It's relaxing. Therefore, it's vasodilating. It's going to cause a decrease in resistance. Well, again, mean arterial pressure is heart rate times stroke volume or cardiac output times total peripheral resistance. Well, here is where you are decreasing heart rate, decreasing stroke volume, and here is where you're decreasing total peripheral resistance. The overall effect is decreasing blood pressure. So you have a return of your blood pressure back. This happens very, very quickly. So this is a reflex, a baroreceptor reflex. But say you're sitting and you stand up really quick and your blood just kind of stays down, pooled in your limbs. You have a little bit of drop in blood pressure. Or you just all of a sudden hemorrhage out a lot of blood because you split open an artery. I kind of like the standing up fast one because it's a little less scary. But in either case, what's going on is you have drastically changed your blood volume. If you're hemorrhaging, you've decreased it. If you stand up too quick, most of the blood volume then drops to the lower limbs, away from your carotid and aortic sinuses that are monitoring blood pressure. In either case, you have a drop in your mean arterial pressure. This then triggers the baroreceptors to then sense there's less stretch. on the carotid and aortic sinuses. And so impulses, since there's less stretch, they're going to increase the number of action potentials. And that's going to stimulate the cardioacceleratory centers and also the vasomotor centers. And so now they're increasing heart rate, increasing contractility. So this is another way of saying increased stroke volume. And so these two together increase cardiac output, because cardiac output is heart rate times stroke volume. And if you increase both, you're going to increase cardiac output. This is due to increase in the number of action potentials from the sympathetic nervous system to the heart muscle and the SA node. So you are increasing sympathetic activity, decreasing parasympathetic activity. You are increasing resistance and decreasing blood flow to GI tract. Then you have also vasoconstriction. So with vasoconstriction, the diameter gets smaller, which increases the resistance, which increases total peripheral resistance. And guess what? Now you have an increase in stroke volume, increase in heart rate, increase in total peripheral resistance, and thus you're going to increase mean arterial pressure, because it's this times this times this, and you get back up to normal. Events in the baroreceptor reflex in response to a drop in mean arterial pressure. If you want to look at it in a flow chart, drop in mean arterial pressure or blood pressure is going to decrease the frequency of action potentials, which is going to decrease parasympathetic and increase sympathetic. Like I said, you're increasing the heart rate. You are increasing the myocardial contraction, which increases stroke volume. You're increasing the diameter, decreasing the diameter of the veins and decreasing the diameter of the arteries. So this is a decrease in diameter via vasoconstriction. And both of those things are going to increase total peripheral resistance and increase return of blood back to heart, because you've increased BP in the venous system. And all of those things are going to bring mean arterial pressure back up. Long-term regulation, again, we get into this in chapter 18. That is going to be controlled by the renal system, the kidneys, controlling blood volume. And so direct renal mechanism is if you create less pee, you're going to increase blood volume. If you pee out more, you're going to decrease blood volume. So controlling blood volumes through the kidneys. Indirect, we're dealing with hormones. Angiotensin II from the adrenal cortex, antidiuretic hormone from the hypothalamus via the pituitary. These are going to affect kidney volumes, which affect blood volume. On the other end, with renin-angiotensin system, this is really an enzyme hormone from the kidneys, which then causes the adrenal cortex to release another hormone called angiotensin II causes the adrenal cortex to release aldosterone. Sorry about that, got ahead of myself. And aldosterone is going to increase the absorption of sodium, which, as we all know, water follows sodium. And so that is to say, it's decreasing urine output because you are reabsorbing of sodium and thus water. And so this increases blood volume. On the flip side, it can, if you don't have angiotensin 2, it can decrease it. But what it's showing here is renin from kidneys release or cause the formation of angiotensin 2. Angiotensin 2 causes aldosterone to be released and antidiuretic hormone, right? So you have sodium and water reabsorption. Both are going to increase blood volume. Angiotensin via aldosterone also causes vasoconstriction. So this is increase in total peripheral resistance. So that's increasing blood pressure. If you're putting it all together, it looks like this, but it's not a new scary chart. It's just the three main factors that are affecting blood pressure is one, blood volume. How much volume is in the closed system? Two, peripheral resistance. How much resistance does the heart have to overcome? And why I say that is because the heart is creating the delta P. And so if you have an increase in resistance, you have to have the same increase in delta P to keep flow, right? And we all know cardiac output is flow, and it has to stay at 5 liters per minute regardless. So flow has to stay the same. If resistance goes up, that means the heart has to create the same amount of pressure as resistance is going up. So peripheral resistance is really driving how much pressure the heart has to make. And then you can also factor in stroke volume and heart rate, right? And so these are the things that are controlling stroke volume, heart rate, which is cardiac output, the third thing. These are the things that are controlling peripheral resistance. And this is the thing that is going to control blood volume. So sodium and water, kidneys, blood volume contributes, blood volume and pressure contribute, different things that are activating the autonomic nervous system. But from all this, what I want you to get out of it is blood volume contributes, heart rate and stroke volume contribute. And then peripheral resistance, how much does the heart have to work against? And those three things are really what are controlling mean arterial pressure. And so with that, we are done with chapter 14.